a senior director of the nanotechnology, nano defectivity and metrology here at Sematech in CNSC, and he has an incredible experience in metrology and semiconductor manufacturing, and working with IBM, several years with IBM. He worked 5 years with Sematech in Austin, and then he came back here to this area where Sematech now is located. Mike has a PhD from Cornell University, close to here, and he has been very kind to come here today with so much work you have just to show these kids what is important about metrology. Okay? Thank you.
Thank you very much.
Yeah.
Let me see if I can plug in now and make this work. Good afternoon, everyone. Yes, thank you for the introduction. So I'm Mike Larsell, coming here from Sematech, where I lead up a couple of centers that we have, one specifically in metrology, one also new one that we're starting up around nano defects. And today I'm going to give a little discussion about semiconductor metrology, talk a little bit about what we're measuring, and I guess I understand some of you are studying some semiconductor fabrication, so hopefully that'll reinforce what you've seen. Describe why it's important. So I'm actually going to throw some economics into this talk as well. So a lot of the stuff we do, the technology is important. I'm a physicist by training. I like the technology. But there's quite a bit behind the economics of why we do this. Kind of give an idea of what we measure in terms of dimensional measurements, then also in terms of finding imperfections or the defect inspection, and then how to characterize those, and then wrap up. So during the talk, I'll give first that background of what we're doing and why, then start to describe a couple of the techniques. There's no way I can describe all the techniques today. This is a very deep field with a lot of different techniques, and I'll do my best to give here a nice overview of what we do. So to start off, just to give an idea of some of the different devices and the complexity that we're introducing as we go forward with semiconductor processing. If you look back a few years and the types of products you would have bought 3-4 years ago, the transistors were fairly straightforward in terms of having a gate on top of a bulk silicon film, few things to measure, dimensions kept shrinking to smaller sizes. I'll come to that later. Just starting to introduce some more complex films within the last few years. So if you buy a state-of-the-art microprocessor today, actually you'll probably be here if you get the latest state-of-the-art 22 nanometer device from Intel. But during time, we've slowly introduced more and more complexity, both in the sense of the materials involved, as well as the structure of the device, making it more three-dimensional, and also continue to also scale the size of that transistor and make it smaller with each subsequent year. So part of what we do in metrology is measuring the dimension of each of these features. Another part is measuring the films and understanding the film quality, and then also understanding how several of these layers overlay. And I'll talk about each of those in the upcoming slides. That's where we are today. We continue to introduce even more complex structures, and I thought this next slide was even better to represent that. As we go to smaller dimensions in terms of the nodes at manufacturing, introducing new materials, whether it is germanium as a high mobility film or like a gallium arsenide film as a high mobility film for the NMOS transistor. Then start to look at how you even thin those down to make tunneling transistors. So the dimensions of the thicknesses of those films will start to reach single nanometer levels. In fact, they already are reaching single nanometer levels back in the earlier dimensions here. And maybe even someday going into carbon electronics and introducing things like graphene or carbon nanotubes, where the critical dimension of all these films is of course, just a few nanometers thick. So continue the dimensional scaling, introduce more complex films, and be able to measure all this. So that's where the industry is going in terms of its technical direction. So today, what you'll see from the state-of-the-art manufacturing, it's about 22 nanometers. So these are fairly high density 22 nanometer structures with the FinFET devices on it, although they still remain silicon. The active technology development today is really around what we call 14 nanometers. That will enter manufacturing probably about 2 years or so from now, 1.5 to 2 years. A lot of research is therefore now being conducted on what comes after that, both in how the makeup of the transistors as well as the size of the transistors. So in order to be able to make this stuff, you have to understand and measure a lot of these properties. And that's really what I'll talk about most today. In the sense of what do we measure in semiconductor manufacturing? Now there's actually two ways you could, or two types of metrology you could think of. I'm going to talk today almost entirely about inline, which is like the manufacturing metrology. So these are things you do when the wafer is running through your process line. Which measurements do you need to measure to control your process? There's another component that I'm not really spending much time on today, which is what happens when something goes wrong. Failure analysis. So you take the wafer, you take it out of the manufacturing line, you take it to the laboratory, and they slice it and dice it in many pieces. And once you do that, once you've broken the wafer into 1,000 little pieces, and they're great at doing that, then you can actually, of course, the wafer is never going back in line. So I'm not really talking about that laboratory type activity. I'm really going to focus on, again, what do we measure to control our process and why? So several different categories there fit into metrology as well. Dimensional. How big are each of the critical structures that you are? So this is just a very simple schematic of what this might look like. So critical dimension, how wide are these lines? The width of that line is really important in terms of determining the speed the transistor operates at, the yield. If they're too big or too small, they may have opens or shorts electrically. Another part of it is there a sidewall slope that can have usually negative. I guess there are not too many cases of positive impact in the process. Not just if it's a line, but also if it's a contact hole, measure how big that round contact hole is. Roughness of the films, I'll show some examples of that. If there's roughness along these lines, usually more in the top-down view, that could be very important. I'll mention some of the techniques we use for that metrology. And another portion of this is overlay. When we're making semiconductor devices today, state-of-the-art devices may have as many as 50 different device levels. So part of it is how do they line up vertically. You print one pattern, you want the other pattern to line up with the previous one. The overlay between those patterns, and that's what we call it, overlay, is also very critical in terms of making sure that they line up. Because if they don't line up, if this contact doesn't land on this line and it lands all the way off, of course, there'll be no electrical contact and that won't work. So you need to be able to measure the position of this layer versus the position of underlying layers. Also, so that's in terms of measuring dimensions. Another one is with regards usually around thickness, but also material properties. So you have a thin film. That film could be as thin as 1 or 2 nanometers thick. So you need to measure the thickness. You probably need to measure the optical constants in some of these films. The composition, if it's made up of a mixture of different materials or doping of different materials, and sometimes also the grain structure, because with these dimensions, if you have grain boundaries going underneath your devices, that can also be a problem. And then a third category I'll talk about today is defect metrology. So this is not so much trying to characterize the sizes or overlay or film thickness. You're looking across a large portion of the wafer and trying to find defects, places where things aren't right. So how do you inspect that, whether it's an unpatterned wafer, a patterned wafer, and then after you've found the defect, how do you figure out what that defect actually is that you can use that feedback into your process to figure out what caused the defect and eliminate the defect as a problem. There are some other categories I had thought about adding today, like in situ metrology, but at some point you just kind of have to keep the scope reasonable. And in terms of the dimensions we're operating today, I thought it might be useful to put a little bit of this into perspective. So the current wafers in terms of manufacturing are 300 millimeters in diameter, so they're 12 inches across. You've probably seen any of those if you've visited the site up in the CNSE site up in Albany or the Global Foundry site in Malta. Next generation wafers are a little bit bigger. They're 450 millimeters, so 18-inch pizzas instead of 12-inch pizzas. But more importantly, if the dimensions we're trying to measure of each of these transistors is, going back to that roadmap chart of about 22 nanometer manufacturing today, is the size of these features are somewhere around 22 nanometers. a little bit of range there because the different layers have different thicknesses. Also, the critical defects, though, the defects that can short out those lines or cause open or anything, are also about 20 nanometers in size. That's the feature you're trying to measure. Of course, the wavelength of light, being a green light at about 500 nanometers, is substantially larger, more than 10 times the size of any of these individual features. The tolerance you want to control that dimension about, is typically about 10% of the size of the feature itself. So that means about 10% of the size, we need control down in the single-digit nanometers. And therefore, the tool that you use, you'd ideally like to, it's not always, you can't always achieve this, you'd like to have the measurement precision be 10% of what you're trying to measure. So that is 10% of the tolerance, and therefore you're down in the sub-nanometer type dimensions. And as reference, of course, a hydrogen atom is 0.6 angstroms, so it would be 0.06 nanometers. So this number here is about 3 hydrogen atoms across. So that kind of gives you an idea of what we're trying to measure in this. And the metrology part's a critical part of enabling the scaling. Here are some of the some recent results out of ASML in terms of characterizing the next generation of lithography technology called extreme ultraviolet lithography, where we are printing dimensions down. You can see here 13 nanometer half-pitch lines. So this is for the next generation technology, 13 nanometer line spaces, contact holes at about 18 nanometers, and controlling the uniformity of the line size to about 1.5 nanometers. So you need to be able to measure 1.5 nanometer uniformity across the wafer. And in the case of the overlay between 2 layers, so if you just take and you're trying to test the machine and you do what they call dedicated chuck overlay, so literally it's the simplest case of print one wafer, take it out, put it back in, and print on top of it, you are in the case of overlay numbers that are about 1.5 nanometers size. So that's what the manufacturing is capable of. What we'll talk about today is how do you actually measure a lot of these. I won't spend a lot of time today on the difference between precision and accuracy, but just a quick reminder, precision means you have good control. You measure the same thing time and time again. It doesn't necessarily mean it's very accurate, because you can have good precision and bad, let's see, whereas good precision and bad accuracy may mean that you're off target. You would like your metrology tool clearly to be able to do good precision, and then you also need a method of being able to calibrate it to make sure that you can calibrate it back to a fixed standard. That's called reference metrology. Again, not something I'll spend a lot of time on today, but you can have a tool that has very good precision, measures the same thing every time, and if there's a known offset, you can actually usually correct for that later. You don't want a tool that has bad precision, or especially bad precision and bad accuracy, because that's something you really can't compensate for. So just a slightly different way of looking at that with regards to precision, effectively is the error bar of the measurement tool. If you take the same feature and you run the measurement tool on the same feature multiple times in a row, how well is that controlled? What's the distribution of those measurements? That gives you kind of some inherent capabilities toward that measurement tool. Accuracy is how you calibrate that to some reference metrology system. If you have a tool being tested versus the reference metrology, you can make some sort of calibration curve. As long as that calibration curve is well characterized and has a good, actually they don't have the R² value of the fit through there, but as long as it's well characterized, you can usually calibrate a good tool with good precision back to a reasonable accuracy. There's another thing that we actually worry about a lot in manufacturing, and it's the matching of different tools. So if you have one tool that makes a bunch of measurements and another tool of the same type that makes a bunch of measurements and it's a little bit different, how do you understand the overall population? So that's really the fleet matching. That's not something that really occurs much in research and development, because usually you only have one measurement tool for each step. But if you're in a manufacturing line and you have a line of tools doing CD measurements, critical dimension measurements, this actually becomes quite an important parameter in itself. Now, an example of how you can use metrology in action. So one thing is can be done is advanced process control, where you take measurements and you directly feed back those automatically to the process to change and make adjustments as you go along. So it's effectively steering as you're driving down the road. So for example, if you have a lithography step that you go and print the small features with your lithography tool, do a measurement before you etch it, do an etch step, do a measurement afterwards, continue on with regards to completing the device, you can actually take those measurements, and if this is too big or too small, you can actually feed that backward to make adjustments for the next lot. That's kind of a feedback loop. The other thing you can actually do is if it's too small or too big here, and you have knobs you can control in the etch tool, you can actually say, oops, actually, this is too small, make my etch a little bit longer. And so that's feed forward type control. Not used as often in manufacturing. Feedback loops are used very often. The feed forward is more like the next generation for advanced process control. And what that really means with regards to your control is, for example, if you're measuring this critical dimension, this line width, and you introduce the APC, you can significantly tighten up the distribution of your measurements post-etch in this case. In this case, you can see about a 30% improvement. That improvement with the average CD and the targeting plus the distribution of those lines means that the key thing you're doing this for is you have more of your devices that are in specification, and you can sell more or sometimes charge more depending on what that business model is like. So this is a direct example of why you would use advanced process control, because you can actually make more things than that you can sell. And this is referring to this cost part of it, which is you have two things you're always looking at, or not always. In the case of microprocessors, what you always look at is what's the yield? What's the percentage of these that work? And then also, how fast are they? Because in some cases, you can, if it's a faster part, you can actually charge more for it. But sometimes if you try to push the process to a faster product, your yield can sometimes roll off. And this was actual device data from, it's not indicated what node it is here. So you need to understand, as you make these variations in your targeting size, what does that mean for your yield? And then, of course, your sales team knows what that means with regards to dollars. So you can start to trade off, yeah, maybe I can accept a lower yield for some of the faster parts because I know I can sell them for more. But you can only really do this is if you know what the distribution of this is and you can track it and understand this trade-off between the yield and what you can sell it for. Another way of looking at it with regards to why you would use metrology or defect inspection as you're ramping up a new product is a time to market. And so again, this is more economics than it is physics, but with a number of assumptions with regards to how you ramp up your wafer starts per month as you start up a new process. So typically you start off with a low number, make sure the process works, you start to introduce more wafers and more products, and you ramp up to a typical fab wafer start per month on the order of like 20 or 30,000 wafers per month, or about 1,000 wafers per day. So the question is, if you're able to ramp more quickly with the same yield, what does that mean with regards to the market value for that? So, and you can actually start to do calculations. The assumptions are always debatable. But as you look through the ramp, if you ramp 3 months faster because of your development cycle, you're applying metrology, or you're using that feedback to be able to make process corrections more quickly, that's $100 million or so type investment. The other thing you can do is what happens if you can yield, this is the die yield now, if you can get to a higher yield faster. So that also, if you do that calculation, it's the difference between this curve and this curve, that's probably another $100 million or so. That's assuming a $15 part, which is probably a little bit on the high side for a lot of the semiconductor parts. And then lastly, if you can actually make your baseline yield higher, so you're eliminating more of these excursions that occur because of problems that come up in your manufacturing line, again, vicinities of $100 million. And of course, these numbers aren't exactly 100 million, but the idea is the reason people do this and the reason people apply metrology is the economic impact is quite large. Another way of looking at that with regards to looking at the measurement capabilities as a function of different device nodes. The key thing from this chart, again, not to emphasize all the details, but as we go to these more advanced device nodes, the return on investment from putting in, or return on revenue loss in this particular chart, by being able to apply more or less metrology starts to increase in its value per node. So the idea of doing this more quickly is not only been important in the past. As we go forward, it's becoming more important. And it's not in this particular study, but even at 32 and 22 nanometers, again, the fact that you can tighten up your measurement error, which controls your process capability and allows you to yield more parts, continues to increase in value as you introduce each of these into manufacturing. And the other way to look at it is on the other side. So how much do people spend? So you may get $100 million per fab in terms of yield learning, maybe even several $100 million. So these are total market sizes. These are not per fab. But you can look at what IC manufacturers actually spend per year on metrology equipment. And just to give a reference point, worldwide, the total wafer fab equipment spending is about $30 to $40 billion. It varies quite a bit year to year. This was as of 2012. I'm sorry, these are 2011 numbers from the 2012 report. So about $37 billion was spent on total wafer fab equipment, and the total metrology is about $4.4 billion. So that's a lot of spending on equipment. And this is just the equipment. And it varies by the categories we'll talk about, but the workhorse in the sense of measuring these dimensions, the scanning electron microscope, this category of tools is about $400 million in worldwide spending. The patterned inspection with optical is over $1 billion a year market. So this is clearly important to wafer fabs. Otherwise, they would never spend this amount of money on steps that sometimes people jokingly refer to as non-value add, because you never see metrology on your finished part. You take your microprocessor out of your computer, metrology never leaves anything behind. It's just used as your process control tool. And yet you spend 10% of your wafer fab budget on metrology. Another key part of this is that really shows up when you go into manufacturing is how many points do you actually have to measure. More measurements means more tools usually, means more spending on metrology. So question is, can you measure every device on every wafer? So I just looked up some approximate numbers from the 22 nanometer node, which is pretty much what's in manufacturing at companies like Intel today. Looking at of course, the size of the wafer and the density of transistors and the number of transistors for the product, I estimated each of these wafers probably has about 600 billion transistors on it. So if you're starting 30,000 wafers a month or about 1,000 wafers a day, which is fairly typical, so you're manufacturing about 600 trillion transistors in a month. And if you were to take 1 second per measurement site, just to do the calculation, if I did it correctly last night, that's about 19 million years to measure every single site. So clearly you're not going to measure every site. Part of this with regards to metrology is understanding how many sites do you need to capture the variations across the wafer. So you'll probably measure a few measurements within each die, a few measurements across each wafer, and a few wafers out of each batch, each lot of wafers. So that really is a complex decision about how to trade that off. It's about your yield targets, your process control, and how fast you have to detect the problem. So typically what you would do in a CD measurement is you're probably measuring a couple wafers out of each lot of 25. You're probably measuring a few sites per wafer, and you're using that as enough of a canary to detect any variations in your process. Early in the process development, probably more likely you're measuring a lot more sites and probably every wafer, because this really becomes a question of, these take time, these tools cost money, and you want to try to make each device as inexpensive as possible. So that's kind of the economics background to why do we spend all this money in metrology and inspection, because it really does affect the bottom line. So now we'll start to talk about some of the specific techniques in each of these key areas, give a little bit of the background about how they work and what we're measuring, and kind of step through each of these examples, starting with dimensional metrology. So in this case, we have these features. These are like representing some fairly high aspect ratio fins that are a few nanometers across, about 100 nanometers high. And so we want to know how wide is it, what's the profile shape, and as I mentioned before, when you have multiple layers, how do these overlay? So the tools that do these, I'll show the details later, like CD, scanning electron microscope, optical measurement techniques, and I show like a tabletop system because the thing you'll notice about most modern semiconductor fabs is everything looks like a white box with a computer in front of it. So there's not really a lot you can see from a photograph of any of these tools. Really what happens, what's on the inside. But these tools typically are running a few $1 million a piece for the state-of-the-art tools. Let me step through all the animation here. And one of the key, oh sorry, that photo doesn't look too good, but one of the major tools that we use is a scanning electron microscope, and I'll describe that on the next page. It's really more than just the line width. This is a top-down view of a device where you have these vertical features. Here are the gates. The underlying regions here look like the active areas, and you're trying to measure the line width. That's a key feature. You're definitely going to measure. You may want to measure the pitch, although that actually doesn't usually vary too much. But then you also are measuring two-dimensional features. So you've designed this shape to have this squared-off profile here represented by the red line. In reality, it's not going to print that way. You can't get that much information through the lithography tool lens. So you're going to want to know what's the actual shape that it turned out to be. That will end up affecting overlay measurements as well. Or whether the line is shortened or whether there's actually pattern parts that are missing. So these are all things you really want to extract as part of your measurement in addition to just the line width. Ideally, you'd like to know the 3D profile, but of course, from a top-down view, that's quite difficult to get 3D profiles from this technique. Now, I'll give you a little indication here of what the CD-SEM is. So, keep the animation off. So one of the primary techniques we use for measuring the width of a line is called scanning electron microscopy. Particularly, it's called critical dimension scanning electron microscopy because it's slightly different than a standard SEM. The physics is identical. It's usually in how it's implemented, particularly with regards to the software. So a scanning electron microscope, the technique, no different than any laboratory SEM. You scan your electron beam across your features. You generate an image. And so the electrons are formed by an electron gun, go through a bunch of fancy electron lenses to land on the target. Then you have a detector that detects the secondary electrons coming off the features. The secondary electrons generate, as you scan across each feature, you're going to increase as you get near the edges of the feature in most cases because the detector's off on the side as you scan the beam across it. And then the CD part of this is you're basically saying, okay, what's the distance between these two peaks? Now, the reason I mentioned precision and accuracy before is, as you can see, depending on the beam conditions, these peaks in the secondary electron emission may or may not directly line up with your profile. But as long as you've calibrated that at least once, you can probably make an estimate if there is any bias between the waveforms and the actual physical profile. Because I guess I should explain that a little more clearly. So when the electrons hit a feature, the secondary electrons come out about the top few nanometers of the surface of the feature. If you get near the edge, of course, you have the electron beam hitting the edge of the feature with more of the beam penetrating and generating more of the secondary electrons here represented by the red arrows here. So that signal that's detecting how many of these secondary electrons are coming off is collected by the detector and used to form the video image. Video image is just like the television signal, I guess the old-fashioned television signals. Scanning the electron beam off, it sees the waveform, it gets a bright feature, and then it makes this picture and then does basically a fit to the edge to determine where the profile edges are. So that's pretty good because it gives you a direct image of what the feature looks like. So you can estimate not only the line width, but you can actually estimate the line roughness as well. So the good thing about this is it gives you, I already covered that. The pros of that is you get a good, and if you calibrate it correctly, accurate image. You get the two-dimensional profile of the complex shapes. You get the roughness in addition to the CD variation. But electrons have to operate in vacuum. That means you do have to put the wafer into a vacuum. That step usually takes a few seconds. So that means it's a little bit slow. It is a complex enough tool that you can't make it attached to your process tool directly. It's always a standalone tool. And the fact that it has to go and scan across this means, and the relatively slow scanning means that you typically don't do too many measurements per wafer. So it's a good technique. It can be accurate. It can give you two-dimensional information, but it has its limitations with regards to its speed. One of the other things about CD-SEM that's a little bit different, I won't spend a lot of time on this, but in terms of optimizing the signal, it's quite dependent on what is the incident energy of the electron beam. So higher energy means the electron beam goes farther into the sample surface. This is a silicon surface, so if you imagine the electron beam comes in here, simulation shows how as it starts to scatter, and where does the energy end up being deposited. So higher energies, like 1.5 kilo electron volts, means your electron penetration's about 500 nanometers. Typically, most of the CD-SEMs are operating at about 500 to 600 volts. You're putting more of the energy near the surface. The secondary electrons that escape are actually only coming from the surface sites. So the reality is if you increase the electron beam, you're putting most of your energy at a place you're never going to see the secondary electrons either. So a lot of the optimization for semiconductor-specific CD-SEMs has been to build tools in this sort of voltage range with low penetration by also keeping the beam very stable. Higher energy is actually easier to focus and control the beam than it is at very low energies. So I think I've described part of this already. This is an imaging instrument. We take the secondary electron signal. We look across a certain field of view. It's usually a fair number of these lines. You can actually take the whole sample sample a few lines and then do the calculation across a few of these lines within the field of view, and that generates your critical dimension measurement. But I think I've already covered most of the basics there. And I talked about waveform in the prior slide. Again, as you scan the electron beam across the feature, it generates the increased signal. And basically, all the CD-SEM is trying to figure out what's the difference between these two peaks. But the problem is, as we go to, I'll skip ahead one slide. The problem, though, is as we go to small dimensions, that scattering area of that electron beam turns out to be a few nanometers. So sure, you have a 25 nanometer feature. And with the right conditions, you get two nice peaks to be able to separate out the width of that. But then as you drop the size of that feature, and these down to smaller dimensions, at some point those two peaks start to merge. And then you have to have more complex algorithms to really figure out what is the real width there. Is it the full width half max of this? Is it some fraction of the full width half maximum? And so it becomes much more difficult in the point where we are today in semiconductor manufacturing, looking ahead as to what might be the future techniques that we use to measure a say a 10 nanometer line. As a matter of fact, if you look, these numbers over here represent the difference between a technique that I'll talk about in a few minutes that uses an entirely different imaging mode, atomic force microscopy, the actual CD as measured by doing a destructive cross-section, and then what is measured by the CD-SEM. So over here, maybe a slight offset between the physical measurements. As you get down here, it might say it's a 6 nanometer feature, where in reality it's a 12 nanometer feature. But another critical thing, the slide I skipped over, is actually the roughness of the lines. 20 years ago, people were less worried about roughness because you had a 1 micron line and you had a few nanometers of roughness, and so a few nanometers of roughness in a 1 micron line is a lot less than 1% variation across the line width. But now, actually, most of the intrinsic roughness of these lines comes from the processing steps that are not scaling with regards to how you can produce roughness, or try not to produce roughness, but end up with roughness anyway. So you still have a few nanometer variation in the line width, roughness across the feature, but now with a 10 nanometer line, a few nanometer variation in the line width is a substantial, tens of percentage variation in the line width. So typically you want to measure those roughness parameters as well. So in your scanning electron microscope, the photo is now rotated, but here's the edge of the line that you're trying to measure. Here is the deviation, the position of the edge of the line, and you can therefore pull out the line edge roughness. That is quite critical for certain things like the device itself. If there's a lot of roughness, it can lead to leakage. Leakage drives up your energy consumption of your device, and it means that your cell phone runs out of battery faster, as I think mine probably needs to be recharged too. Line width roughness is another thing. This actually does also affect the speed of the transistors. It's in a slightly different form with regards to how it affects the device. It does lead to timing issues, so that is actually critical as well. The difference between line width roughness and line edge roughness is the edge is a single edge of the feature. Line width is the correlation across the two edges of the feature. In some cases, this one is important. In some cases, line edge roughness is important. At least the useful thing out of the CD-SEM is with one physical measurement, you can extract both parameters. So, CD-SEMs, as I mentioned, this is kind of the summary slide. The good thing is you get a direct image of what the feature looks like within the limitations of the electron beam. You measure individual features, so you drive to an individual transistor and measure that transistor. You get the complex shapes from the two-dimensional nature of the image. And it's very rapid. It's slow in manufacturing because you have to transfer in and out of vacuum. But if you have a new process and you're doing process development, it doesn't really take a lot longer to load a wafer and start to get pictures of what your device looks like. So, as I said, this is about a $400 million market because this is really the workhorse of the industry. The problem, though, is you really can't get the three-dimensional structure of the feature very easily. People have experimented with tilt beams. They've actually looked at how you can tilt the beam and get that information, and it doesn't work very well. That's why it's not used regularly today. You only are measuring a few features, so you're hoping by measuring a few features you're getting enough sampling to represent your device. So you're not getting a large number of features. You're measuring literally tens or maybe hundreds of devices on a wafer that may have 600 billion transistors. Sometimes it can cause sample damage from the electron beams, particularly with regards to organic materials like the photoresist. It certainly does change the line width of the photoresist as you measure it. It's also fairly expensive with regards to what it costs compared to the next technique I'll talk about. And it can be very difficult to measure a lot of features if they are very deep or very high because you need to be able to extract the secondary electrons out. So it is heavily used in process development. But there's also an alternative that is widely accepted in the industry, slightly different method. It's used mostly for process control, and I'll explain why. It's a fairly simple technique where you bounce light off of a grating target, and then you measure the spectrum of the reflected energy. So it's good. It's basically just a grating type scatterometry. It's called scatterometry. It's a scattering type measurement. The good thing is it's a fairly simple technique in the sense of what the optics looks like. Calibrating the signal back to the shape is a little more difficult, and I'll come to that in a second. The downside, though, is you need a target. You need specifically a target designed to scatter the light back towards your detector. This is an optical technique, so these tools are not in vacuum. These tools are almost always just in atmosphere because it's a light source that's operating pretty much in the visible spectrum. The good thing about this is if you build a complex enough model, you can actually start to get the three-dimensional features of your shape. Because each of these layers and each of these shapes reacts differently with the light, at different wavelengths. So you can often extract not just the line width at an average point, you may be able to extract the top, the middle, the bottom, if there's little films on it, if there's films underneath. In theory, you can build up a complex enough model, actually we're beyond 5 to 7 parameters now, to be able to start to extract a lot of these dimensions off of the films. So it's really a powerful technique and used in many cases for process control, but it does have some disadvantages that I will describe on this slide. So the good thing about this is, as I said, it's a simple scattering technique. It really, you bounce light off the grading target, you measure it, you get a spectrum. It's about as easy as you can get for inline process control. Sorry, I went the wrong way. So the advantage is it's light-based, so it doesn't usually damage the sample. It's fast, it's not in vacuum. It samples a fairly large area because you have this target you're bouncing it off of. That target contains a lot of features, so you're automatically doing some statistical sampling across a fairly large area. You can extract profiled information. Sometimes the tool is simple enough that you can put some of these basic ones attached to your etch tool or attached to your deposition tool and get real-time feedback information. So it doesn't even have to go from the etch tool to some other bay in your process line. You may be able to do it right on the tool itself. And they're also typically less expensive than SEM systems, although the vendors are doing their best to make these expensive as well, it seems these days. The downsides, though, are you have to have a target. So you specifically have to make a target on your wafer that you use. You have to build a model to be able to extract that spectrum back to the physical feature. That is actually very time-consuming. It's very good for generating supercomputer sales, but it takes a lot of effort to be able to correlate that complex electromagnetic scattering back to what the physical shape is. So typically you have to run a bunch of test targets of known dimensions, build up a model, and then you can use it for inline process control. So that's actually where it's typically used, is not when you're developing a new process, but you have something running in manufacturing, it's running fairly stable, you characterize what the sample looks like, and then you use this technique to make sure it doesn't drift off of that point. The fact that it's also less expensive than CD-SEMs also is advantageous to fab managers who don't like to spend more money than they have to. So it's typically used for process control. There's another technique that's been developed. It's not used nearly as much in terms of manufacturing, but it is used significantly in development because it's a powerful technique. It's called atomic force microscopy. What this is, and it actually sounds incredibly simple, but you have a small probe on a cantilever, and you drag that probe across the surface and watch how that probe goes up and down. Sounds fairly straightforward, but you actually can sample atomic level variations in the surface by this technique. So it's fantastic. This is the tool people use for measuring surface roughness most of the time. The technique is fairly simple. You're dragging this cantilever across the surface, measuring its deflection, usually by an optical technique, to be able to pull out effectively what the surface profile is in the vertical direction. So this can be an incredibly powerful technique to be able to measure atomic layer roughness or measure, in some cases, the critical dimensions of features and start to extract a lot of that same profiled information out. But it has some downsides because here's an example where you're measuring with the AFM a number of these lines, and as you can see, they're kind of tapered. The question is, are they really tapered? Well, that's the reason that's a question is you're measuring with a physical probe. And so the sample image that you see is actually a convolution of the shape of the original image and what the probe looks like. So in theory, you can pull out a lot of this information, but the problem is these probe sizes are typically 20 to 30 nanometers, and therefore, as you get down to 20 or 30 nanometer dimensions, it can be very difficult to measure in between the lines. So the reality is probably this edge is measured fairly accurately, and this one is in between is probably not measured fairly accurately. So that's why this is typically used a lot in process development to figure out what's going on in your process, but less often used in manufacturing. So that was the measuring a line size and measuring a line profile. As I mentioned before, another critical part of dimensional metrology is measuring how well two layers line up. And you have to do this because you have 50 or 60 layers sometimes in a modern process. Here's an example of a fairly old microprocessor, but it already has 8 levels of metal. And so you need the alignment between each of the metal levels and the metal and the via levels and the metal level and the transistor down here. Those all have to be controlled within nanometer scale precision. So if you have variations, here's an example of a misalignment where the line up here is slightly misaligned and you start to see you're missing the edge of the contact. And if that becomes too small, then you'll end up with a shorting between those two lines. Or an open if there's not actually another feature there. So this is a very critical. We typically measure that both like in the X and Y displacement of the 2 layers. Now, how is this done? This is also typically done with an optical technique. Usually you use a feature that you print on one layer, and then you print another feature, usually like a box inside a box or something like that, on a subsequent layer. So for example, often you don't have the corners of the box. You just use the inner part of the target. But you have the red, imagine that was printed on, blue is printed on the previous layer. This layer on the reticle, on the mask, you have another structure that's printed inside the same target. And then optically, you're basically measuring the difference between these lines. That can be done fairly accurately. And by comparing, therefore, the position of each of these lines, it gives you the displacement and, therefore, the overlay. Now, sampling here is also very important because there are, the big difference between doing process development and monitoring. Here's an example of a wafer that has been measured with 5 sites and 5 measurements per site. So in each one of these scanner fields, you're measuring the displacement and the corners in the center, and you're doing that at several sites across the wafer. Now that gives you a basic understanding of, it looks like something has shifted in the Y direction down, is particularly toward the top of the field. That looks to be somewhat characteristic across each of these sampled fields there. So that would give you some information, probably to go back to look at the scanner overlay. But again, throughput is tied to the sampling strategy. You can sample many more points. There are some examples, I can't remember, I guess I didn't stick it in here, of sampling thousands and thousands of points across the wafer to get detailed maps. But that takes a lot of time, and of course, time in metrology is expensive. So you try to typically capture the fewest number of points needed to understand if you have a problem. That is also a difference whether it's just a linear or a quadratic or cubic type variation. So I didn't want to say too much on overlay. That's typically not one of the more cutting edge. It's a very critical measurement process in the fab today. The tools for actually doing this optical characterization are actually pretty good. Now, to talk a little bit about films, which is another critical aspect, is given these complex devices, if you have a high K gate stack, you have multiple films in here, you have your junctions formed by implants, implanted ions, and you're trying to measure, how well can I control each of these processes that are used to develop and deposit these different film stacks. That includes the thickness, that includes sometimes the optical properties. It also includes sometimes, where's the example up there, whether you have dopants in there. So like metal oxides, you may not just have hafnium oxide. There may be other things in the stack. The atomic layer deposition processes usually are a complex type of precursor, different materials in there. How do you make sure you're putting down a film that is the right physical dimensions and electrical properties that you need? So to do that, there's a lot of techniques. In fact, it seems like every time we go to a new device node, we introduce some new techniques. So I'm not going to be able to talk about all of these, but we can get thickness measurements by, for example, optical techniques, and I will describe the top few of these. You can get some of those with similar application of X-ray techniques. I'll give an example there. You can gain some measure of the elemental composition, so which metals or which dopants are within there by similar techniques. Sometimes you want to measure the stress of the film, stress and strain. That's actually quite a complex and not well developed part of the metrology suite. Sometimes you need to know the roughness, and sometimes you need to know the crystalline or electrical defects as well. But first, I'll describe maybe one of the simplest techniques, which is ellipsometry. So this ellipsometry in its basic sense has been around for quite a few years. The idea is you take a optical light beam. Typically it's a either single wavelength or small number of wavelengths of light. You run it through a polarizer. So you know the polarization coming in. You bounce it off an optical surface that causes, by interaction with the elements in the different layers, it causes that rotation of that polarization, and then you measure how that polarization changes coming out. So when I was in grad school, we had a very simple one of these. We had a helium neon laser. We had a thing for adjusting the polarization. You have your sample, you bounce it off. You have another polarizer to measure the polarization, and it's a fairly simple technique, except that we've made it more complex because we want to measure many, many different layers, try to get the optical constants out of those different layers, and sometimes with a single wavelength of light, that's not enough. So part of the spectroscopic ellipsometry, which is an extension, is you're not shooting in one wavelength of light. You may be shooting in either a broadband spectrum or multiple wavelengths of light and measuring those in terms of the output polarization in each one of those wavelengths. You can also do it by scanning the angle, and so by adjusting all these parameters, you can take a fairly simple technique and make it quite complex. So here's my picture of what an ellipsometer looks like. You have a source of light that's typically would be unpolarized. If you're using a laser, it may start off polarized. You cause and introduce some polarization. You see how that polarization changes as it bounces off the sample, and then you detect basically what the change is in the polarization. The problem, though, is so that works fairly well as long as you can bounce light off of this and the light is sampling through your substrate. The challenge, though, as we introduce new devices, as I showed on the first 2 pages, is we don't have the whole periodic table in our devices yet, but sometimes I think the device engineers are trying to fit the whole periodic table into there. 20 years ago, you had silicon, you had oxygen, maybe you had a little fluorine, you had a couple of dopants, and you probably had aluminum as your metal. But now we introduce a substantial number of different materials, which I didn't easily mark on here to point them out, but there's a lot of different materials being used. Those are not always optically transparent, particularly in the metal cases down here. So you may need to use a different technique. So how could you sample that? Well, instead of using optical light, you can go to a shorter wavelength like X-ray. This is an example of X-ray reflectance, and that's what XRR stands for. So you have an X-ray source, in principle like the one you have in your dentist, but probably a little bit more monochromatic. You have a certain number of optics to focus that on the surface. You bounce the X-rays off the surface. They, of course, penetrate deeper into the substrate, if it's particularly if it's a reflective film in the optical. And then you measure the scattering and you measure the reflectance of the spot. Not shown on here, you can also measure some other properties out of that. You can measure the diffraction, which gives you some idea of the crystallinity, and you can measure things like fluorescence, because as the X-rays hit certain atoms in the substrate, they emit photons and different energies, and you can detect those and start to get more information about the properties of the film. And then in a little more detail, you have the incident light coming in. You're looking at the reflected X-rays from different points where it's interacting with the surface. But I think I won't go into detail there. So there's a wide variety of ways of sampling both optically active and reflective films. Those are just a few key examples. But next is another one that I think is fairly interesting and a little bit different dimension is around defectivity. So now we're switching gears from doing measurements to inspecting larger areas of the silicon wafer. The idea is across your wafer, you have a number of different dies. You're trying to find wherever there's a defect. Those defects cause yield problems, and you want to find out how many defects you have, as well as how do you reduce the number of defects. So every time you run one of these wafers through a process tool, it would typically pick up a few defects. You want to make sure it doesn't have the tool doesn't become very dirty. If the tool becomes very dirty, you'll quickly end up with zero yield. Because as you can imagine, if this were the example of what the wafer looked like, and you had to go through 50 different device layers, and you put 50 of these stacked up, what's the probability that any of these little individual boxes are going to not have a defect by the end of the process? And the answer is probably 0. Statistically, you can calculate that. So ideally, you're looking for wafers where it's a low number of added defects. You know where they are, and you can react to them. And there are several different techniques for doing that, and I'll explain those in the next few slides. But first, I'll talk a little bit about, here's the slide that explains, if you have a few defects on your starting wafer, you print your gate structures, you do the gate lithography, the gate etch, you start to build up. That Intel chip I showed had 8 metal levels, but the reality is a lot of them today for advanced microprocessors probably have 10 or 12 type of metal layers. So if there's a few defects in each one of these, chances are when you get to the end result that a lot of these dies are not going to function. So part of that yield learning that you do with defect inspection is you're doing measurements at each step and then trying to correlate them at the end to the electrical nature of the device performance as well. So this is an example of what might happen within a process tool that you're trying to control. So what happens is this is a plasma deposition chamber in a highly schematic form. You're forming some sort of plasma with the different gases introduced. They land on the layer to build up, or land on the wafer to build up a layer of, for example, oxide that you're trying to deposit. However, inside of plasmas, there's quite a few defects. They're formed by sometimes the plasma reacting with chamber components, sometimes it's nucleation of defects within the gas phase, and so, or it can even be handling the wafer in and out. If your robot scrapes against something, you're going to scrape a lot of particles onto the surface. So typically, you're not going to have 0 defects when your tool is running well. You're trying to sample that by sticking in a bare wafer every once in a while, doing a simple inspection, counting the defect density. Obviously, this is, if it's number of defects, this would be an integer, so this is defect density. So you may have a couple spikes here. Those are probably measurement errors more than anything, but you want to be able to detect when something starts to go out of control. That's probably reflecting, okay, your robot has shifted, it's now scraping against the chamber, or one of your electrostatic chuck down here is starting to break down and shed particles. So you use this type of technique as kind of the canary to say, oops, something's wrong, I better go find this tool and see if it's clean. And this is another example of building up defects, so I think in the interest of time, I'll skip over that. So you try to put all this information together. You're trying to do several things with the data your data that you're collecting when it comes to defect inspection. You're trying to find out if your tool's bad. You're trying to find out if there are characteristic things that are occurring in your process. That some of these may be related to the tool. Like this signature on the edge typically reflects if there's a door or something over here, probably causing a problem. These are probably scratches. You may end up with some defects that I mentioned are nucleation defects. Unfortunately, I don't have any of them there. So you're trying to take all of this data and find out, you correlate these spatial distributions, the number of counts at each step, the trend across the different wafers, and trying to put that together to achieve higher yield. And so I'll explain a little bit about some of the techniques we use to collect these types of maps, and then also what you need to do to analyze the defect afterwards, because that is a key part of the yield learning as well. So you have a bunch of defects here. You can go and look at them later and try to figure out, okay, it's not that I have defects here. What is it? What's the composition? How do I pull out what the elemental values of that defect are? If it's stainless steel, it's probably a lot different source than it is if it's hafnium oxide or something like that. So these actually therefore fit into different spaces, much like the metrology tools for the CD measurements, but also it's even a little bit broader, because you have several different techniques that work well in different spaces with regards to throughput as well as the sensitivity and what it can detect. So throughput here, this is measured in wafers per hour. There are some techniques that are very, very, very fast, but they're only looking for very big defects. So the prime example is whenever your laptop screen is dirty and you hold it up to the light at an angle and you see all these little dust particles on it. I mean, that's roughly how these tools operate. So they can be very fast, but they don't detect small defects. There are methods of doing steps along here to get maybe a little bit less throughput, but a little bit better resolution. Optical techniques, technique I'll talk about called bright field inspection. It's a few wafers per hour if you're inspecting the whole wafer, but you get a substantial amount of information. You can actually go to electron beams, very similar concept to the CD scanning electron microscope. It has very sensitive detection, but it's also very slow. You typically don't use that for full wafer inspection. And then there are other ways where if you're not inspecting a pattern, you can actually simplify your process and get fairly high throughput, fairly good detection, but it's only used for bare substrates. So it's good to check to see if your tool is any good. So that's kind of how these end up being applied. Is this one is checking to make sure your tools don't get dirty. This is doing a routine inspection across a fairly large sampling of wafers. You're sampling a smaller number of wafers with a more sensitive technique, and you're probably using electron beam inspection only in the technology development. So how do these tools sort of look on the inside, highly simplified? So the first one I'll talk about is this, what we call bright field inspection. It's basically an imaging technique. Effectively, you have light bouncing off your wafer. You're measuring what the pattern looks like, kind of like a digital camera, and looking to see wherever there's a defect that is generating a picture that doesn't look like it's supposed to. Highly simplified, because somehow they can put enough complexity into these that to make them fast and to have high sensitivity, you need very good optics. You need actually, it's not a PC, it's actually almost a supercomputer attached to it these days that take the pattern and maybe do a pattern comparison between two different die to try to pick out what the defect location is. So it is not particularly fast, relatively low throughput. As far as optical tools go, it has the best capture rate. Typically now these are multi-wavelength type tools. That makes the optics quite a bit complex. And then the data analysis is also a substantial part of the price that ends up making these fairly expensive tools in the fab. But they actually do very well in terms of identifying defects for process development. So here's an example of what the output might be, courtesy of the largest maker of one of these tools, is you're trying to characterize on your different wafers what the defects are and obtain some information about what it might be in terms of its composition. Whether it's a scratch, and I'm sorry you can't read those numbers, but those are about like 30 or 40,000 scratches on these wafers, so that's a substantial problem. Whether it's a defect inside the film, whether it's a bump on the wafer, some residue, etc. So this is the type of information. You're looking at a fairly large area on the wafer to pull out a substantial statistical distribution of what these defects may look like. Now that's too slow for most people in manufacturing, so they developed another technique. It's also optical. It's called dark field inspection. Fundamentally, it's looking at the scattering off of the surface. So it's not really trying to image it's doing some imaging, but it's not trying to do a full imaging of the wafer. It's more, let's bounce light off of it and see what doesn't get reflected back toward us. So that's the dark field part. Bright field means it's reflected back and captured by your camera. So it's faster. You can scan more quickly. You can put different detectors around, and that's what these Ds represent. So it's fairly faster, and it's used for inline excursion detection, and it can use patterned wafers. So here's an example of a dark field detection. You're inspecting each and every lot that comes through your process line. Before I showed what was an analysis of a single wafer, and you may be testing different process conditions to see which ones generate defects. And that's what this particular example showed. So we have the one on the right here is you made some changes in your process from the top to the bottom, and it started to generate more defects. Or you may be looking at your process control in line, where you're monitoring each and every lot. Oh, we have a problem. Let's go and see what that is. So that's typically what the application of a dark field inspection tool would be, probably running at about 20 wafers an hour, sampling a fair number of wafers in each process condition. There's another variation of that. It's also dark field. It's a simplified version of that previous tool. It's for unpatterned surfaces. So basically imagine you stick in a blank silicon wafer and you want to see how many defects have landed on it. So you're not trying to do any imaging at all. You're only trying to detect scattering. So it's typically a lot faster. So you have a light beam coming in, you're measuring the dark field scattering coming out. Whenever there's a particle, oh, it scatters, and I see a dark field signal. That can't be used for patterned wafers, though, or can't be used well for patterned wafers. So it's often used only for doing tool characterization. So you're running your process wafers through your process tool, and then maybe once a day you go and stick a blank wafer in, pull it out, and do an inspection here. So it only takes the time on the process tool to do one wafer. The throughput of this can be 40 to 60 wafers per hour, and it's relatively inexpensive, so it's a good method of trying to determine if your tool starts to cause a problem, but it doesn't really ever be able to give you information about how different process steps work together. It can also be very sensitive to changes in surface roughness or residues left on the surface. And here's a particular example where one of these maps, and this is even using a little bit of a patterned wafer, you're not trying to image the wafer and find the defects, you're just looking at this scattering map. And what you can see is that this particular step, was leaving a residue of the photoresist on the wafer. With that scattering map on an unpatterned wafer or a patterned wafer, it can be fairly quick to start to identify what can be very small variations with regards to residues on the surface. Lastly, with regards to inspection tools, is the one that is, for all intents and purposes, the same as the CD-SEM that I showed before, except now it's scanning across much larger areas trying to find defects. It can even do some things called voltage contrast, where you're looking for shorts and opens in a device. So it has very high sensitivity, probably about 10 nanometers for the state-of-the-art tools now, but you're taking this electron beam and scanning it across the surface, and so it's never going to be very fast. You never use this for a full wafer. This is the type of tool you would only use for sampling a small area. So it's highly used in process development when you're developing something new. Sample a small area, look to see if there are any changes. Probably not to be used very often in process control, except maybe in some unique examples where it can pull out electrical information that the other tools cannot. So that's why, even from a market standpoint, this is the smallest of the inspection tools. So those tools are all the process of, okay, I have a wafer, I found some defects on there, I know there are defects there, that's usually not enough. The next thing you really want to do is figure out what that defect is actually, what's its source. So what is it actually, what is the physical representation of that defect? These tools, typically also based on scanning electron microscopes, are called defect review SEMs. They take the maps from these other tools. For example, they may take this defect map and then have that coordinate system and then go to that defect and take a picture of what that defect looks like. That already gives you some indication of what the source of that defect may be. If it looks like a flake from maybe something coming off your process chamber, or nucleation defects are typically very spherical. It allows you to get some information from the image itself, as well as the other thing that these types of tools add that are not on CD-SEMs are usually some method of elemental analysis. This refers to energy dispersive X-rays. When you put an electron beam into a solid surface, you not only get secondary electrons, you actually get some X-rays generated. Those X-rays are quite characteristic of the materials involved. So by looking at that, you can actually look, for example, if you're just doing nitrogen, or in this case aluminum, here's what your SEM image looks like. Well, let's also take the signal from the X-rays, plot the one from aluminum, and you can start to see, well, this is an aluminum line. It looks like we have some sort of nitrogen-containing defect on top of it. In that case, it's my guess, it's not listed on here, but we use a lot of like titanium nitride and tantalum nitride, or silicon, even silicon nitride films that could make up that. And so it gives you some idea of the composition of that defect. If you looked at this and you saw iron and chromium, well, probably it's stainless steel. So this is a good way of being able to go and look at some of these defects, tell you what that defect is, review it, give you an idea based on its shape and its composition, what the likely source of that defect is. Problem is it's relatively slow. It actually has very high resolution because it's the same as the electron beam, the scanning electron microscope, but it's relatively slow, so you would be able to sample maybe 100 defects per wafer. If you have thousands of defects, you probably are not going to go and drive to every single defect. So it's, again, trying to give you enough information with the right sampling to make some decisions about how you can change your process control. So here's an example of doing the elemental analysis. So your defect tool said, I have a defect here. This is what the defect looks like. Oh, look, so it's a nice little bump there. That's pretty convenient. You go and do the composition map, and you start to look at the elements that are contained there. You are, of course, going to see the underlying surface. And this is kind of a strange map. I guess I can't figure out exactly what that defect is, but there's a lot of iron in it. Good chance it's probably a metallic defect coming from somewhere in your process chamber, so like a mechanical interaction between the different components. So that's useful, although even this is limited by how small it can look at. As I said before, it's about high resolution in imaging, about 5 nanometers, but X-rays actually have a fairly large interaction volume. So what do? There are methods of going down below that. So here's an example of SEM and EDX. That's the same technique I showed before. If it's a fairly big defect, this is about 70 nanometers, it's carbon, it's oxygen, it's setting on silicon, so we expect to see silicon. So this is probably an organic defect. What if it's 25 nanometers? Well, 25 nanometers, if you try to do this with EDX, you're going to probably only see silicon. You're probably only going to see the background signal, and any sort of additional information is likely to be lost. As I said at the start of the talk, I was going to talk mostly about inline tools. Here's the one example. I'll talk about an offline tool, because this is one of our ongoing challenges is, this technique we know is limited from its elemental composition. We can get information about these defects if they're smaller. These are taking them offline, so these are semi-destructive techniques like transmission electron microscopy. If we can find a way to make this an inline technique, this is an extremely valuable technique, because here's an example of about a 25 nanometer defect sitting on top of a multi-layer surface, and it's fairly easy to pull out from the TEM that iron, chromium, it's probably stainless steel. Here's a signal from ruthenium that you can't quite, you can see it on my screen, but it doesn't show up well in the projector. The ruthenium goes over the top of the defect, gives you an indication where it occurred in the process step as well, between the deposition of this layer and when you put the ruthenium on top of it. Or another example, this is one that's underneath a big layer of a multi-layer stack, where we can see there's actually some lead content in this particular defect. So there are techniques of being able to pull out higher resolution nanometer scale imaging. However, unfortunately, we haven't found a way to make them inline techniques yet. There are many other ones I'm not going to talk about today, since you probably already heard me talk enough. In terms of future, there are ways of replacing the scanning electron with a helium ion. As you're scanning across the surface, fundamentally it looks the same as a scanning electron microscope, except you're using helium 2+ ions. These are highly surface sensitive. As you can see by this structure, you're pulling an incredible amount of information out of the surface of the structure. Unfortunately, sometimes the helium ions are somewhat destructive. So some applications are starting to use this and see if it's a future imaging technique. On the optical scattering, again, maybe you go from optical wavelengths, visible wavelengths, to X-ray. So we have an active program effectively doing that scatterometry approach with X-rays. So you shoot your X-rays through your grating target, you measure the diffraction, and you can pull out information at even smaller dimensions. Hard thing is generating enough X-rays to make that practical today. So again, it's not used anywhere other than in some laboratory techniques. Or other things, like maybe today people are starting to look about defects around the edge of the wafer. Defects that may be right near the top of the wafer, on the very edge, or even on the backside. So those tools are also starting to come into use. Usually based on the same types of techniques I showed, either like a dark field scattering or imaging technique, but deliberately trying to do it across a surface that may not be specularly flat. So a lot of opportunities with regards to metrology. It's driven really, starting off by the reason we do this is yield. Yield usually results in how expensive it is to make your parts work. So the process control is critical. Yield learning has been part of the semiconductor industry for many years. It's really enabled by metrology. That metrology becomes more and more expensive. It's not, these tools are not cheap. These are typically few million to tens of millions of dollars a tool cost per tool. But as I showed in that economic analysis, you can quickly make that up when you can get hundreds of millions of dollars back in your yield ramp. Dimension, size control, we have two methods. Either we try to image the surface, where we pull out a lot of two-dimensional information, or a scattering technique where there's a target that's deliberately designed to measure the dimensions. We measure a lot of film techniques. As we introduce new materials, we've gone from all optical. When people were looking at silicon dioxide, you used only optical techniques. As you go to these complex high-K gate stacks with hafnium oxide and lanthanum and tantalum nitride and tungsten and all these other films in there, you have to start introducing X-ray techniques or others. Around the yield learning with regards to the random defectivity, defect inspection, many different techniques really optimized to the application, high throughput, low throughput, process development, detecting variations within your manufacturing line. So it's kind of like finding a needle in a haystack, a 20 nanometer defect in a wafer, and then figuring out what that needle is actually made of. So this is kind of an interesting field. It's one where you say you never actually end up on the finished product. However, there are investments of billions of dollars a year on these tools, and it's for a reason. It's because it really goes back to you're trying to achieve high yield and good process control. And so that's really the reason for doing a lot of the development in semiconductor metrology and continuing development, is because people actually do tend to listen to yield, because that does mean dollars. And so a lot of investment in metrology. It is a significant enabling part of the semiconductor industry. Thank you for all for your attention, for sitting here for over an hour. Appreciate that. Thanks.
Any question for our presenter today?
No? Yeah. Do you make your own tools, and do you only test your wafers?
No, so most of the tools I showed today are commercial tools. So there are companies that build them. A couple of them, more in the evolving, these new techniques I showed at that second to last slide there, some of those are ones that we've built. Because the role of Semitech, our job is an R&D consortium. So we're not trying to compete in the volume CD-SEM market, but we are trying to do something around the X-ray scattering techniques. So in that sense, we do some work on building our own tools, but most of the tools I showed are commercial tools that you would buy from large companies like a KLA Tencor out of California, or Hitachi out of Japan, or Applied Materials has a division that does this as well.
Do you only test your wafers, or do you test any other? If somebody else, if another company has problems with wafers, or there's defects, or there's a problem with the system or whatever, do you inspect other wafers?
So Semitech, yeah, that's a good question. So Semitech's a little unique because we're a consortium, so we do actually test a lot of other wafers. We, in fact, even build some test samples that we send to some of these equipment suppliers as well. But we're working with several of the metrology companies where they want to test our test samples. Or sometimes when we have a tool here, one of our member companies will send us wafers to test. If you're looking at a major company like a Global Foundries, they wouldn't typically test anything but their own wafers. The Semitech model is different. We're a research consortium. Our job is really to try to push the semiconductor industry forward. So as we build that test stand for the CD X-ray scattering, we are deliberately asking for some of our member companies to send samples to test.
Do you charge a price for that? Is that a way to pay for your tool? Is that another way to pay for the tools? Or?
So it goes back to the Semitech consortium models. We have member companies who pay yearly fees to support Semitech. And so it's not so much on a sample-by-sample basis. It's more, we have member companies that support us, which include the big fabs like Intel, Samsung, TSMC, Global Foundries, and IBM. So they kind of pay us yearly, and then we do that. And then we also sign up equipment companies, and so we do it less on a charge per sample and more on a yearly membership fee.
technician working in metrology, what kind of skills do you think they need? I mean, looking at this stuff, it looks, you see things, you know, and need a little math?
Yeah, actually, that's a good question. I would say for people who are, it depends separating out people who fix tools versus people who use tools. I think I'll start with the user of the tool. Their statistics is very important. I kind of glossed over it at the start, but this question of how many sites you sample and what information are you pulling out about variations, there's a lot of statistics there. So I think that's a key part of it. The user should also have some idea of what they're trying to measure and why. So that's kind of some basic semiconductor processing. If you're looking for overlay variations, it kind of helps to know if it's a metal and a via level that if you miss, it's going to have a short. That kind of helps you understand what the problem is, or maybe from the litho tool, what might be causing the problem. So those are some of the skills that I think are useful for the technician who is doing process development and using a metrology tool. The other side of it is if you're looking at technicians who fix tools, it's going to depend on the technique. The E-beam techniques, vacuum skills, being able to work on vacuum systems, keep them clean, know how to fix those, fix turbo pumps, fix flow control valves, that sort of thing. If it's E-beam, certainly being able to do calibrations on they're usually electromagnetic focusing optics that are in the E-beam column. You probably don't have to sit there and wind coils yourself, but you should understand the basics of how it works. Or if it's an optical tool, optics background really helps. Again, you don't have to understand all the physics of the scatterometry, but understanding the polarizations is important. Understanding how light sources generally work and what you would need to do to fix those. So those are some other useful skills as well. I mean, it's a wide variety because metrology is not like physics, where I was trained in. Metrology is this cross-disciplinary thing where you may need some skills in electromagnetics and optics and computer techniques and statistics and be able to apply those broadly. That answer?
Yeah, so what kind of, technicians at Semitech, right? I mean, as people, not, and you know what kind of backgrounds they're coming from? Is it totally like widespread? You can have chemists, you can have electronics, you can have physics, I mean, is there... I'm talking to these guys who are taking the semiconductor manufacturing and electronics.
Yeah. For metrology, it's probably less of the things like the chemistry. It's probably more like, since you're sampling with various sorts of electromagnetic beams or charged particles, the physics is usually fairly important. Understanding a little bit about the electronics and electromagnetics is often one of the strongest things in the metrology space. Again, if you're working on a process tool like a CVD reactor, that's probably more chemistry. But in this case, around metrology, electronics and physics and electrical engineering type applications are probably the most valuable. And I don't want to de-emphasize statistics. So.
What technique we're going to have in 20 years from now when nanotechnology will be prevalent,
Well, so the current trend is it seems like you keep adding on more and more techniques. So it seems like you have everything you had before and new stuff. 20 years, if you have to look at something like carbon electronics, some variations on the techniques I mentioned, but things like X-ray probably wouldn't work particularly well on carbon. So you're probably going to have to look at very exotic optical techniques like multi-wavelength types approaches. Probably a lot of things based on variations of the AFM, atomic force microscopy, because that actually, with that, sometimes you can sample out electrical information if you do that correctly. I just showed the simple profiling application, but there are things called conductive AFMs where you start to sample electrically across the surface. There are even some very fancy ones that are just laboratory today where you're actually doing a Raman spectroscopy with the AFM tip. So I think those are the types of things we'll see more and more of. Maybe some variations on the charged beam technology. So we've actually looked at some other ideas as well. So the helium ion that I showed. There are other variations out there where you can start to look at things that become more surface sensitive. Electron interactions with materials, I showed, electrons can penetrate microns into surfaces, which is useless if you're trying to measure the top 1 nanometer.
Are we going to have less defects in nanotechnology or no?
Which?
Less defects than
Oh, less defects? So you said less defects?
Are we going to have less or more defects?
So what we've seen with some stuff I didn't show here is when you count defects as a function of size, the general trend is the number of defects goes up roughly as the third power with the decreasing size. So probably more defects would be the answer. So we did some, we have some various counting techniques, more like the in situ counting, where literally we sampled at 50 nanometers, and then we went and sampled at 25, and the number of defects jumped by 7 or 8x. So really close to somewhere, but people debate the exponent, but the simplest thing to think about is if you have a 1 micron defect and you break it up into smaller chunks, the volume is scaling as r cubed. So the number of defects in that same volume is probably going to go up roughly as a factor of dimension cubed, which is a problem.
What's being done with the roughness? You said that wasn't so much a problem when the gaps were bigger. Is that more of a surface tension issue where roughness isn't scaling down the same way that everything else is scaling down?
Something like that. Part of it's probably also the polymers that are used in photoresist, that they have these photoacid generators there, and that those acids diffuse a few nanometers. So when they're hit with light, what you're deliberately trying to do. And so you've probably always had that kind of, based on the material, a few nanometer roughness in your line. It's just more evident as you shrink it. So you asked, what are people doing? So there's a couple things. They're trying to engineer the materials, the photoresist materials with different compositions to try to minimize that in the beginning, or find ways you can smooth it after you've generated it. So if you have a rough line, particularly if it's high frequency roughness, is there a way you can smooth it? And there are some techniques people have looked at for doing that as well. So it's a combination of engineering new materials and trying to apply additional techniques for reducing the roughness.
Okay, there are no more questions. Thank you very much for being here.
Oh, thank you. Appreciate it.
I hope the students learn something today. I'm sure they will.
Well, if they have any questions, they can send them my way.
Perfect. We will do.
Okay?
Well, okay.
Thanks.